So for this video, we're going to be talking about hydraulic fundamentals and Pascal's law. Hydraulics, of course, is going to fall under the larger umbrella of fluid power, where we use a fluid to transmit force. Now, the fluid could be a gas or a liquid. It doesn't really matter, both work. But in this case, because we're talking about hydraulics and specifically we're talking about automotive brakes, we will be looking at hydraulics, right, with using brake fluid to transmit force. One of the the fundamental law of physics that goes along with that is what's called Pascal's law. And this is a law that mathematically explains the relationship between three different factors. Those factors are force, pressure, and area. The calculations that come along with this will allow us to find any one of these values as long as the other two is known. It's very similar to Ohm's law when we talk about electrical. So when we're talking about force, the force that we're talking about in our calculations are either going to be an input force or an output force. And we're going to look at this in terms of either pounds or kilograms. Depending on whether we're working in imperial or metric. With area, I'm going to skip over pressure here for a second. We're talking about the effective area of pistons, right? So this could be input or output. It doesn't really matter. And like I said, this could be input or output. And pressure, we can define this as the force that we apply spread out over the available effective area of the input piston. Now, mathematically, what this formula is going to look like is something like this. Typically, we put it in a triangle, so we're going to put force on the top, represented by F. We're going to put P and A on the bottom, and then we're going to draw our triangle. So where F equals force, P equals pressure, and A equals area. When we want to use this formula, actually apply it. If we're going from top to bottom, this is going to become a division question. And if we're going to go side to side, this is going to be multiplication. So for example, in order to use this to solve for force, what I would do is cover the F up. What I'm left with is pressure and area, and because they're side to side, I would multiply them. What that means is if I take a known pressure value and multiply it by a known area value, the answer to that equation is going to be the force. If I'm looking for pressure, all I got to do is cover up the P. I'm left with force and area. I take my known force value, and I would divide it by my known area value, and then the answer would be pressure. And similarly, if I'm looking for area, cover that up, take my force, divide it by my pressure, and the answer is going to be the area. So the next thing we're going to talk about is Pascal's law. Now, Pascal's law states that a force applied to a confined fluid will transmit undiminished and with equal force on equal areas and at right angles to them. So I kind of want to break that down and make sure that we all understand exactly what we're talking about here. And to do that, I've drawn a cylinder here. So this is, a syringe or a big turkey infuser for a deep fryer, pretty much anything, right? All we have is a cylinder here. We've got a piston inside, and we've got a rod that's going to allow us to put some force into it. Here we've got an outlet, so we could pull this back and suck fluid in, and we could push it forward, and we could blast fluid out. So if we look at the first part of Pascal's law here, it says a force applied to a confined fluid will transmit undiminished. Right? So when I'm talking about applying a force, this is the first part of the top part of that triangle. So if we put that in, just to remember what we're dealing with here, we got force, pressure, and area. And of course, pressure and area are interchangeable here. As long as they're on the bottom, it doesn't matter where you put them. Just I always have a tendency to put the P on the left-hand side for whatever reason. So the force in this case would be the input force. And the input force would be input through the end of the syringe. right? So if I wanted to put an input force here of, doesn't really matter what it is, right? We'll throw some numbers on it afterwards, but for right now, let's just say input force. Going to be in this direction, and that's the first part here. So we have a force, and we have it applied to this piston. Now, if we assume that this is full of fluid, right, the next part says applied to a confined fluid will transmit undiminished and with equal force. Now, we've got a bit of an issue here, okay? Because of that word confined, the fluid that we are applying the force to in order to use hydraulics properly has to be confined. And while it will be housed inside this cylinder, if the end is open, it's not really confined, right? There's definitely going to be a restriction here. So I'm not saying that we can't make any pressure at all, but what I am saying is as we move this piston forward, any fluid that's inside, although there will be a little bit of pressure built in the cylinder as a result of the resistance to being able to get out, it will get out. So once it gets out, there's no pressure left because there's no more restriction. Right? So in that case, we're going to have to do something if we want to really use this as a hydraulic system. So what we're going to do is we're going to expand on the system. We'll put a pipe on it, and we'll turn it this way, because we can do that. One of the wonderful things about hydraulics is we're not constrained by shape. If we can put a line there, we can make it work. And then we can put another cylinder here. So I'll just do this really quickly. This may not be quite as neat as the one that I drew up there, but it'll be the same thing, same idea. Like that. And then I'm going to put another piston in here. Like that. This one's going back this way. And we'll put a push rod on this one as well. And this push rod will end up being our output once we're all done here. Okay. So now we have a closed system here where any force that I apply to the fluid contained in here is going to be applied to the back of this piston here, and we're going to get some movement out of it. Right? So we have a force now, we have a confined fluid, and it says it will transmit undiminished and with equal force on equal areas and at right angles to them. So what does that mean? Right? Equal force on equal areas. Well, this is where we got to start to throw some numbers down on this thing. So if we look at our input force and we give this, again, you know me and my nice easy numbers, let's say 100 pounds. Right? I like to work in multiples of 10 just because it's easy and I don't have to think about it that hard. So if I put 100 pounds of force in here, this system is completely full of fluid. All the force that I put in is going to be transmitted to the fluid. But the sticky part here is equal areas, right? So to know how much pressure I'm going to get inside, because all that pressure is basically the spreading out of that force, we need to know how much area we're dealing with on the input side and on the output side, right? For pressure, we only need to know on the input side, but for force, we're also going to need to know what we have down here. So how do we figure that out? Well, all we got to do is basically use area of a circle formula to figure this out. So if we put a diameter on this piston, and again, let's make it real easy. Let's make this a 2-inch diameter piston, right? All we have to do is figure out the area here. Now, I used the term before, effective area. What effective area means with regards to hydraulics is we'll have a 2-inch diameter piston, so when we figure out our area calculation here, we'll know what the surface area of this is. And on this front part of the piston, all of that is effective area because there's nothing taking up any of that real estate. But on the back side of the piston, you would have to do the same calculation, and then you would also have to subtract the area that's taken up by the push rod, right? So even though the size of the piston from front and back is the same, the effective area on the back side of the piston is lower than the effective area on the front side of the piston. In this particular system, it doesn't matter at all because these are both what we call single acting cylinders, right? We're actually going to make the cylinder move this way, and that's going to create something. We're not ever applying pressure to the back to make it move with hydraulic force. We're doing it mechanically. So effective area in this case is going to be the entire area. That's what we're talking about here. So if I want to know the area of my input piston, it's just area of a circle. So A, we're going to use pi r squared, right? And of course, we need a radius. We have a diameter here, but just to review, the radius equals d divided by 2, right? So we have a 2-inch diameter, which gives us a radius of 1 inch. So our A is going to be pi, which we'll only use to 2 decimal places here, so 3.14, multiplied by radius, which is 1 times 1, giving us an area of 3.14 square inches. Okay. So now, I know what my area is, and I know what my force is. The next thing to figure out here is the pressure, right? So we can do the math first, and then we'll come back and we'll talk about what that actually means. So according to my law here, Pascal's law, it says pressure, that's what I'm looking for, so I'm going to cover it up, is found by taking force and dividing it by area. So down here, we're going to go P equals force divided by area. And if we expand that out, P equals 100 divided by 3.14. Solve for P with our trusty dollar store calculator. 100 divided by 3.14 gives us a pressure of 31.847133. So I'm going to call that 31.85 psi. 31.85 psi. Now psi is the unit here, and of course that means pounds per square inch. This is where the area comes in too. So what does that mean, pounds per square inch? Well, we are putting in 100 pounds of force, which means 100 pounds of force is going to be transmitted through the fluid, undiminished, right? We're not going to lose anything here. But with equal force on equal areas and at right angles to them, right? So what that means is this piston has 3.14 square inches of surface. We have 100 pounds that we're putting in. We have to divide it by the surface area here, right? It's not that we have just strictly 100 pounds coming through. That 100 pounds has to be divided by every square inch that we have. In this case, we have to divide it by 3.14, right? And that's going to give us our overall system pressure of 31.85 psi. Now, if I get this out of my way for just a second, not just a second, I'm erasing it's going. What that means is the pressure inside this entire system is now 31.85 pounds per square inch. What that means is in this direction and at right angles, in this direction, in this direction, this direction, this direction, everywhere in this contained system, we have 31.85 psi. 31.85 pounds acting on every single square inch that we have within this circuit, which means that we also have 31.85 psi acting on the back of this piston, right? So if I want to see what we're going to get out of this, what I would have to do, we'd be looking for output force of this piston here. And we know force is pressure times area. So we would need to know the area of this piston, and then we would take our system pressure and we would do the math, right? We would multiply it out. So this is a smaller piston. Let's call this one 1 inch in diameter. We need to know the area again, and I'm just going to give myself a new place to work here. We're going to use the same formula. A equals pi r squared, 3.14 times, in this case, 0.5 times 0.5. A equals dollar store calculator. 3.14 times 0.5 times 0.5 gives us 0.785. Inches squared, right? So that's the effective area of this piston down here on the backside. So if we want to know the output force of this push rod, and again, I'm just going to give myself another little place to work here. My force, pressure times area. Pressure is 31.85 times the area, which is 0.785. We're getting a little cramped there for space. I apologize for that. So we're going to go with 31.85 multiplied by 0.785, and we're going to end up with 24.21725. I'm going to call that 24.22 pounds. Okay. Input force of 100 pounds, output force of less than 25 pounds. So what happened here? Well, we decreased the size of our piston, right? If we break that down to what that means, again, is we've decreased the surface area that we have. So we had 31.85 pounds acting on less than 1 inch, right? If this was a 1 square inch piston, I'm talking square inches here, we would have got 31.85 pounds of output. If we would have doubled it to 2 square inches, we would have doubled our output. So this is kind of the relationship that we have here. Now, the interesting thing to note is, even though as far as force output goes, we have decreased the force output. What we have done, or what we are able to do here, depending on the size of the piston and the cylinder, is we can increase our stroke, right? And the reason we can increase our stroke is, even though our force coming out of it is much lower, if we look at the volume of fluid between these two cylinders, right? The diameter is double in this one than it is in this one. So that means that the fluid required to fill these cylinders, if the length was equal, right, you need twice as much for this one. So what that translates to is, even though the output force is lower, the movement, because of the increased volume of fluid, you can actually get more movement out of it. So depending on the system that you're designing, that may be a desirable thing, right? Maybe you don't need a whole bunch of force, but you need to move something pretty far. So this would be a setup that you could use for that. If that wasn't the case, if we wanted to reverse that and we wanted to make this piston bigger, because what we were after is output force, right, which is in the case, in a lot of the times the case with brakes, we would use a much bigger piston with a much shorter stroke. So if you look at the brake system on your car, you have a master cylinder piston that's relatively small, 3/4 of an inch or something like that, maybe 5/8 of an inch. And the output of your calipers in a lot of cases are, 3 inches or bigger or better. So we're going to get a lot of force multiplication in that case, because we're going to make a pressure and then we are going to apply it to a bunch of square inches, right? The surface area, or the effective area of that brake caliper piston, is going to be much larger than the surface area of the piston that made the pressure. So the output force is going to be very, very high. But because the diameter is so much bigger and we are constrained by the amount of fluid volume that we have in the smaller cylinder that's causing the pressure to be created, the amount of movement in a linear fashion back and forth is going to be very, very small, right? Which is okay for brakes, because we really only need to apply them, a fraction of an inch to get them to stop, and then we pull them back with the seal of the caliper, and we're in good shape. So this is basically the relationship between the thing, right? We're talking about a force applied to a confined fluid. That's going to be the input force. The fluid is confined because the system is sealed, right? It's going to transmit undiminished, which means if we put 100 pounds into it, we are going to transmit 100 pounds. But with equal force on equal areas, we have to spread that 100 pounds out over the area, the effective area of the piston, right? That's applying the force to the fluid. And it's going to be on equal areas and at right angles to them. So if we're creating a pressure of 31.85 pounds per square inch, that means there's 31.85 pounds of force acting on every square inch within the system. So last thing we're going to do here is we're going to take the principles that we learned about mechanical advantage, and we're going to put it together with Pascal's law to kind of see how this very simple brake system that I've drawn here is going to work. So we've got a brake pedal here, which consists of a class 2 lever, a push rod. We've got a piston that's going to basically act as our master cylinder, and we got a single channel out to a brake caliper here, which again has a single piston in it. So the first thing we need to do is figure out the mechanical advantage of this lever here. So of course, the mechanical advantage requires us to know the length of the effort arm and the length of the load arm. So first we'll look at, again, we're just going to make some arbitrary numbers here. Let's get an effort arm first. So the effort arm would be from the fulcrum to the point of input. That's going to be our effort. And we're going to make that, let's say, 15 inches today. And then we need to know the length of our load arm. So the load arm, again, from the fulcrum to the point of output. And today we are going to make this 3 inches. Right? So to figure our mechanical advantage out, we're going to use the same formula that we used last time. So mechanical advantage equals the length of the effort arm divided by the length of the load arm. Plug in our values. MA equals effort is 15 divided by 3. Therefore, our mechanical advantage is going to be 5 to 1. So now we know that. Another things that we're definitely going to need to know is the input force, right? We're going to need to know the input force of the pedal, how to relate that to the mechanical advantage, which is going to give us the output of the pedal, which will also be the input to the cylinder, right? So this is where we want to make sure that we know 100% what we're talking about here. So we're going to go, let's say 10 pounds input force. To the pedal. So the driver is actually stepping on the pedal with 10 pounds of force. So we're going to say pedal output force equals driver input multiplied by mechanical advantage. So pedal output force equals driver input of 10 pounds multiplied by the mechanical advantage of 5 to 1 equals 50 pounds. Right? So we've got 10 pounds coming out here. We've got 50 pounds acting here. Right? 50 pounds acting on the back of the piston in the master cylinder. Next thing we're going to want to know is how much effective area do we have in this master cylinder? So if we give this a diameter of, well, again, just to be easy, let's say 1 inch, right? We need to know the area. So we can go like this. Let's call this step 1. Calculate the mechanical advantage. Step 2, we calculated our pedal output force, which is going to be our input force for the master cylinder. Step 3, calculate piston area. I'm going to call this the master cylinder, so MC piston area. And we know A is pi r squared, which is going to give us 3.14 times 0.5 times 0.5. And I just did this, but I can't remember what the number was. So 3.14 times 0.5 times 0.5 equals 0.785 square inches. And then we're also going to need to know the effective area of the piston for the caliper as well. So we'll call that step 4. Caliper piston area. Same formula. Pi r squared, 3.14 times, well, we don't know because we never gave this a value, but let's call this 3 inches. So the radius, of course, would be 1.5 because we just divide that by 2. So we'll go 1.5 times 1.5. A is 3.14 times 1.5 times 1.5, giving us an area of 7.065. So I'm going to call that 7.07 square inches. So now I've got all the values that I need, but I'm out of space. So I'm going to just bring in another piece of paper here, and I'm going to write a few things down. So we know the master cylinder piston area. Move that up here. So we just figured it out, 0.785 square inches. We know the caliper piston area. Was 7.07 square inches. We know the input force at the master cylinder, which, remember, was the pedal output force. Was 50 pounds. and now we're ready to figure out everything else, right? What the end game here is, what we want to know is how much clamping force do we have with this caliper? So we're going to bring up Pascal's law, force, pressure, and area. We know both areas and we know the force, right? So the first thing we're going to do is we're going to figure out how much pressure have we got in this system, right? So to calculate the pressure, it's going to be force divided by area, and we're making the pressure here. So this is going to be our input force, so we're concerned with the area of the master cylinder piston at this point, right? So P equals force divided by area. We've got 50 pounds of input force divided by 0.785 square inches. That's the area of the master cylinder piston. That's going to give us a system pressure of 50 divided by 0.785 equals 63.694. So let's call that 63.69 psi. Okay, system pressure. So when we push on this piston with 50 pounds of force, the resulting system pressure on every surface inside the system, right, at right angles and straight and everything else, everywhere, every square inch, is going to be 63.69 psi. If I want to know the output force, so the caliper piston output force, it's force. I need the pressure multiplied by the area. F equals P times A. So in this case, F equals the line pressure that we just made, 63.69, multiplied by the piston that we're looking at, the area of that piston, right, which was the caliper piston. So we're talking 7.07 square inches. So let's see, 63.69 multiplied by 7.07 is going to give us an output force of 450.29 pounds. So in this case here, because we had a small piston making the pressure and the output was a large piston, we're getting a multiplication, right? And this is very similar to what we're going to see in the actual braking system of the car. So just to kind of break this down one more time, we've got a mechanical advantage through the pedal assembly, which allows us to put in 10 pounds and get 50 pounds out. That 50 pounds of force is going to be applied to the piston in the master cylinder, which is going to apply that force to the fluid, but it's going to be spread out over the surface area of the piston, right? So in doing that, because the piston has a value, an area value of less than 1 square inch, right, at 0.785, the resulting system pressure is going to be higher than the input force, right? So we ended up with our pressure. I've lost it on the page here. Anyways, our pressure inside of 63.69 psi, acting on every square inch inside. And of course, it's acting at 90 degrees and everywhere else, it's also acting on the back of the piston. But that is going to be applied to every square inch of that piston. And because we ended up with over 7 square inches, it's going to be multiplied by 7.07 to give us an increase in force on the output.